What's up, everyone? Welcome to the CVPR pre-show sponsored by Voxel 51. I'm your host, Harpreet Sahota, a hacker in residence at Voxel 51. I'm joined by my co-host, Jason Corso, co-founder and CSO at Voxel 51, and a professor of robotics, electrical engineering, and computer science at the University of Michigan. Today, we're here with Sebastian Koch. Sebastian is a third-year PhD student at the Ulm University and Bosch Center for AI, where he is supervised by Professor Timo Ropinski. We'll be learning about Sebastian's paper, Open3DSG, Open Vocabulary 3D Scene Graphs from Point Clouds with Queryable Objects and Open Set Relationships. Open3DSG is a novel method for predicting open vocabulary 3D scene graphs from point clouds. It enables zero-shot identification and description of arbitrary objects and their complex relationships using features from vision language models. I hope you're excited as I am to talk about Sebastian's paper. Let's jump right into it.
Thanks for having me. Thanks for a nice introduction. As you already introduced, I will talk about our work Open3DSG, which is an open vocabulary 3D scene graph generation method that predicts scene graphs from point cloud with queryable objects and open set relationships. The task of 3D scene graph prediction is basically going from a 3D representation, such as point cloud, to a graph-based representation where the nodes in the graph are basically objects in the scene, and the edges in the graph are basically relationships between the objects in the scene. And so far, this task was mainly solved by supervised learning on predefined classes, for example, by 3DSG, Scene Graph Fusion, or VLZ, which are all presented as CVPR in previous years. They defined like a set of known object classes and known relationship classes, and then they had the supervised loss to predict these, which worked definitely great. But of course, this kind of limits the expressiveness of the scene graph when you only have a small closed set of classes to describe the object and the relationships. In our work, we asked the question of how do we get this to a more open vocabulary setting, which definitely has the advantage of predicting 3D scene graphs that are much more expressive. So here, for this small example, like a usual supervised method, it would probably predict, like for the TV and the wall, that the relationship would be on because it was trained on this on class. What would be great is to have a mounted on relationship. This is, of course, much more expressive. And for a human who wants to maybe get the TV off the wall, this would be, of course, much more informative. And this is exactly what we are trying to do with this work, predicting open vocabulary scene graphs that are not supervised on a closed set of classes, especially for these relationships. And we basically do this by leveraging the progress in the 2D domain. So what we are doing is basically we want to distill features or the knowledge of multimodal large language model into the 3D domain. Because so far, these multimodal LLMs, they usually only worked on images. So what we are going to do is in these multimodal large language models, usually they consist of an image encoder that perceives the world and language decoder and LLM to output the reasoning. So what we are going to do is we cut the connection between the encoder and the decoder, and we are distilling features from this image encoder into our Open3DSG network, which takes as input the point cloud and then outputs like a feature representation that's in graph form. And these features in the graph, they live in this digital language space. So we can pass them to the LLM, which then can give us prompted relationship outputs. So if I want to have the relationship between the backpack and the bed, I can just ask the LLM and it will give me the answer based on the perceived graph features by our method. A little bit more in detail. So basically we want to learn this graph neural network, which takes in the point cloud, then uses a graph neural network to basically have this graph feature representation. Then we basically have two supervision signals here. The first is basically for objects, for the nodes in the graph. So this is this node supervision law. So basically what we do, we project this point cloud into the image space that's aligned with the point cloud. And then we encode all of these images with a vision language model here, OpenSec, to get basically this visual feature embedding of the objects, which is aligned with language. And then for basically the edges in the scene graph embedding, we use exactly this kind of splitting of the LLM. So this BLIP here is a feature encoder of the instructed BLIP model. So similarly, we now take a bunch of images which basically show pairs of objects and also encode them with this feature encoder, and then use a distillation loss such that the 3D model approximates the features from 2D preceding encoded. And then at test time, in the first step, we can basically predict the objects in the scene graph by querying like arbitrary classes and reducing the feature graph to a graph that has known or that has queried object classes. You can see this here. So now we already predicted the object classes, and then we feed this predicted partial 3D scene graph with known object, but still feature embeddings for the edges into the former and LLM together with the already known object classes. And then we can ask the LLM, what's the relationship between these two objects, or what can I do with these two objects? And this is what the LLM then will give us as output. For example, here for the 3D scene, we have the pillow lying on the bed, and this is exactly what the LLM will give us. And how this will look now. So here I have an exemplary scene, and here's our scene graph prediction. And what I want to highlight here, same relationship from the first slide. Basically, our model is able to predict that the TV is definitely mounted on the wall, but we can do much more with this. So for example, in a completely zero-shot manner without having to train this, we can also predict attributes for a certain object node. So for example, this is not any dining chair, it's actually a padded dining chair. Or this is not any wall, it's actually a concrete wall. So this is quite nice. We can have these zero-shot applications. But we can also go for something like affordances. So same like before, we embed the scene into this graphical representation, can then use the LLM to prompt to give us relationships. But we can also do more higher level reasoning. For example, we can ask the LLM, could I lift object X from Y? For example, here we have this pillow and the bed. And so the question is now, can I lift the pillow from the bed? Actually, the LLM, based on the basically 3D conditioning of the scene, it can say, yes, you can lift the pillow from the bed. While, for example, a counter example here is that you cannot lift the bed from the carpet because the LLM says a bed would be way too heavy to lift it. Yes, this is basically our method. We can do many zero-shot applications. So basically, whatever you want from the LLM, you can basically get it. If you have a creative question, go for it and ask the LLM, and it will give you like a simple response in this graphical manner. Yes. And if you have any questions now, feel free to ask.
Awesome. Thank you so much for the overview of the paper, Sebastian. Appreciate that. I'll see if Jason has any questions.
So many questions. It's so good. So I really like the application you show here, like affordance prompting or like general querying. Like you're almost enabling this ability to do like physically grounded queries of point cloud scenes, right? I think that really fascinating and fantastic. But basically, you don't actually train anything in your approach, right?
No, we definitely train this GCN. This GCN is trained to imitate the vision features of the 2D vision language models, which then have the language kind of counterpart. And so it's tasked to basically, for any arbitrary scene, it is tasked to imitate what the 2D perceiver would embed. And so this will do our 3D model, except that it actually can perceive 3D point clouds.
So ultimately, that means that so it is open vocabulary, but it's also not open vocabulary in some way, right?
We are only as open vocabulary as the 2D models that we want to imitate, right? And then the second thing that limits our open vocabulary is, of course, that we do this distillation from the 2D to the 3D model. Of course, we won't distill the entire knowledge of the 2D model into our 3D model because something we maybe miss in our training. So there's definitely a more specific knowledge in our 3D model, but generally it is almost as open vocabulary as you can get it.
It sounds to me like you actually also have a different method for semantic segmentation of point clouds.
We basically just pre-process every point cloud that we have, which with a method called mask3D, which is actually very excellent for basically predicting class agnostic masks of the point cloud. So we do not care what the method will say, like this point is a bed or something. We just want to know which points together cluster into one instance. And this is actually almost solved for these kind of masking networks. Like predicting the class is much more difficult, but like grouping points together in a shared instance, this actually already works quite well.
This is more of a general question for the sake of people who want to do work like this. Why do you use both BLIP and CLIP and not just one of the two of them?
So this BLIP, QForm, and LLM, this is basically one model that we split up. So basically this multimodal LLM, it's called instruct BLIP that we use, and we cut it in between. So this BLIP encoder is basically the receiver part of this multimodal LLM. This is why we use BLIP here. And for the OpenSec and CLIP, so CLIP is an awesome model for this kind of open vocabulary classification. So we definitely wanted to use that. And OpenSec is basically CLIP, but so CLIP works on like entire images, and it will give you a feature embedding for the entire image. OpenSec is like CLIP, but it gives you feature embeddings for each pixel that is then aligned with CLIP. And we use this advantage of basically, because we can project the point cloud into the image space, and then we can just aggregate the feature embeddings from OpenSec that lie the pixels that basically are, or the points that are projected into the pixel space. This is why we use OpenSec. But instead, you could also use CLIP and get the feature embedding for the entire image. But we found that only using the feature embeddings of the pixels that actually correspond to the object works a little bit better, because this way we ignore background, for example, much better.
I have not worked much with point clouds and this type of data. Like, how common are data sets with aligned point clouds and images?
It is quite common actually, because usually all 3D datasets are basically recorded by somebody going through the environment with a camera and a depth camera, and then reconstructing the point cloud. But the catch is, of course, that you want high quality image frames. And there we actually had quite a lot of problems to getting a dataset that has the high quality alignments of the point cloud and the images, especially also images that have a nice field of view that actually show pairs of objects where you can get the relationship. And so in the end, we opted for ScanNet, which is definitely a state-of-the-art dataset, but we definitely would like to extend this to more dataset, make the distillation part here a little bit more robust.
Would you imagine it's plausible to have a point cloud in a more sort of like idiomatic image of the type of scene, right? Like a bedroom scene or a cafe scene or an office scene, and still achieve the same functionality?
So as long as you have a decent field of view and we can still determine different kinds of objects in the image, I think that works. The real challenge is, of course, that to get like a good embedding into our 3D network, the embedding has to be good from the 2D network. So if the 2D network can work with the image, then our 3D model will learn from it.
If there's practitioners out there looking to apply the findings, what are some practical steps or considerations they should keep in mind? And do you think there's any specific scenario use case that this method will shine the most?
The big advantage is that our method is open vocabulary, so it should transfer to domains quite easily without having to retrain it. So like a good start is, of course, to just take our checkpoint and see if it works in your domain. And I have a good confidence that it will definitely work quite well. Where it shines the most, I think, is definitely in the indoor scenario, where you can observe lots of relationships between objects and get like a very fine-grained understanding. And I think this is also very important for robotics, like robotics that have completely different tasks sometimes. With these open vocabulary scene graphs, they can actually quite easily adapt to their scene representation by just querying different classes or different prompts of relationships.
Awesome. Thank you so much.